Today we're going to work through an example using Gauss's law to find the electric field outside of a plane of charge. So we'll draw our infinite plane of charge, like so. And we know that the electric field will come off above and below our plane of charge, vertically straight up and straight down, based off the symmetry of the plane. In this case, we can choose a Gaussian surface, which we call a pillbox. And this exploits the rectangular symmetry of the plane, and we have that the pillbox is half above the surface, and we'll say that it has area A, and then it will also extend below the surface. Just draw some dashed lines. And below it will also have area A. And so this Gaussian surface is what we're going to use to find the electric field above and below the plane. We are also going to use Gauss's law in its integral form, which says that the electric field dotted with the infinitesimal area vector is equal to the enclosed charge over epsilon naught, where this enclosed charge is the charge enclosed by the Gaussian surface. To finish off, we'll say that the infinite plane of charge has uniform charge distribution, which we'll say is sigma. Let's start with the right-hand side of this equation. So we want to find what the enclosed charge by this Gaussian pillbox is. So we can say that the enclosed charge is the integral of our charge density sigma over the infinitesimal area dA. So by looking at this charge distribution, we can say that because sigma is uniform over the entire plane, we can pull it outside of the integral dA. And then instead of trying to figure out what the sides of this pillbox are, we know that the surface area is simply A. So this integral is going to be sigma times the area A. And we'll just use this general area A for now, because later on it will cancel out with the other side of the equation. Now let's work with the left-hand side of this equation. So once again, we're going to exploit the fact that the electric field and the infinitesimal area vector are moving in the same direction. So we initially said that the electric field is straight up and straight down away from the infinite plane of charge, and the infinitesimal area vector is going to be that on our Gaussian surface, which will also be straight up and straight down away from the plane of charge. However, now we have to recognize the fact that because our Gaussian pillbox has this shape, and the electric field is moving straight up away from the plane of charge, it's only going to pass through the top and bottom if we include the underside underneath the plane of charge. It will only pass through straight through the top and the bottom of this Gaussian pillbox. What that means is that we'll actually have no electric field passing through the sides of our Gaussian pillbox. In this case, when we have our electric field, it will be parallel to our infinitesimal area vector. So we just end up with the magnitude inside this integral again, and then we can end up with the closed integral is the magnitude of E times dA is equal to the enclosed charge over epsilon naught. And what this means here is that the electric field will still be constant at the top and bottom surfaces of our Gaussian pillbox, but because we need to include what's above and below the plane of charge, we'll actually end up with twice the electric field. So we end up with 2 times the magnitude of the electric field times the closed integral of our area dA is equal to the enclosed charge over epsilon naught. And this 2 comes from the fact that we're including above the plane and below the plane. And then this area integral, again, since we're just considering the area of our Gaussian pillbox, this closed integral will just be A. So we end up with 2 times the magnitude of E times the area A is equal to the enclosed charge over epsilon naught. So now that we have these two equations, let's plug Q enclosed into the right-hand side and work through to find the electric field. So we say that 2 times the magnitude of the electric field times the area A is equal to the enclosed charge, which we'll say is sigma times A over epsilon naught. So once again, we notice that the A's will cancel, And this goes to show that it doesn't matter which area for the Gaussian pillbox we choose, in the end, it's going to cancel from both sides. And we can solve through for the magnitude of E, saying that it's sigma, the charge distribution, over 2 epsilon naught. Now, in order to find out what the direction of this electric field is, we said before that it moves straight up and straight down from the infinite plane of charge. And we denote this by using what's called the normal unit vector, sigma over 2 epsilon naught. And we denote that with simply n hat. And n hat is a vector that moves perpendicular above and below to the plane of charge. Yeah, indicating that the electric field will move straight up or straight down. So our electric field is equal to sigma, the charge density, over 2 epsilon naught times this unit vector n hat.